Okay, so on the last video, we were discussing about continuous function, and also we discussed about this conditional function. So I said to you that um, we can adapt this example to a real world problem. And before we start to discuss about our, before we keep going with our content, which is today, sorry, on this video, we will discuss about linear functions. And before that, I wanted to try to adapt this problem to a real world problem. So we are trying to adapt these problems to financial problems. Like I say that to you on this example that we can use like for example for a fixed income. So for example, if we have a fixed income and instead of face this as a function of x like we are doing, uh, we need to we can adapt to a function of time. So right here, let's say for example, instead uh, is 2, we have, let's say 2000, and let's say this is a 2000 reals because we are in Brazil. So we have a fixed income of 2000 reals, and right here instead of use x again, now we use the a base time t, and we can have hours or days or months or even years. Okay, so now the problem grows. Um, we were able to adapt to a financial problem. So we are saying that we have this fixed income. So let's say right here, let's use months. So we got month 1, month 2, month 3. So we got this fixed income uh, of 2000 reals on 1 month and 2 months on month 3 and so on and so forth. It's fixed. But let's say on the month 2, for some reason, this fixed income it got interrupted, and we can say that uh, by this tiny circle right here that in functions we say that is a discontinuity. So right here is a discontinuity, discontinuity. And we are doing this analogy instead of say that is is a discontinuity. We are saying that this fixed income it got interrupted for some reason that at this first moment we don't need to approach to discuss. And what I wanted to call your attention right here is the power of the signal processing. Because just uh, one point, it doesn't mean nothing to us. The only analysis that we can do is, the only conclusion that we can take is, we can say that on the month two, our fixed income, it was interrupted. So we don't have on the month two this income of 2000 for some reason that we don't need to point to approach right now. But when uh, signal processing, which is what we wanted to approach right here, is for large amount of data. So large amounts of data. Okay. So uh, we we need to got more points. So um, we don't need to um, guys stuck it into this only point, uh, which is best uh, to us to take a conclusion to. Let's now grow this problem. Let's say now that instead of uh, we are using maps. So let's say we got 100 points, but now distributed in 10 years. So we can have 100 points. This point right here, it's called P1. So 100 points. I don't know, 100 points. So we have something like P1, P100, or even PN. And is distributed, let's say the 100 points is distributed in 10 years or in years. So if we do this, if we approach this problem this way, we can create a new data, a new type of data. This way, we create a new type of data. And we can do other type of analysis, take a conclusion. So um, let's say on the year one, we got um, 2 or 3 months with this discontinuity. So instead of and we cannot do this by hand. This is something that we can only do by a algorithm. And yeah, we can made up a algorithm to calculate this. Is looks like a geometric progression. And after made up this algorithm, we can pass to a computational algorithm, so we can compute, um, for example, using the Octave environment. Okay, I'm just making up this this example just to show to you why we are trying to build this intuition in functions. Okay, and that's it. Let's continue with our content. On this video, we will discuss about linear functions. Okay, so we have a function um, of the real numbers, which is injective into other um, a set. This is a set, and this is other set of real numbers. And this arrow, it means that is injective. So we have a set of the real numbers which is injective into other set of the real numbers. And let's say that f of x is equal a times x, and this a is the linear coefficient. Okay, very simple. And just like we have been done all this time, what we would do is attribute a values to the x, which is we are creating a relation between the domain and its image. So right here, what we are doing, for example, for right here, for each value of the domain, we will get the same value on its image. So right here is the domain, and right here is the image. So we can still do this. So -2, -1, 0, 1, 2 on this set A. So let's say a function of A, which is, well, this function of course is not injective, because for different values of the domain we got the same value on the image. So it's always returning to this two value. Not injective. Okay, so right here this function is injective, and again let's attribute in some way that we can cover symmetrically the x-axis. So we got this linear coefficient which is positive. Uh, on this case that we will discuss right now. So for minus 2, we got minus 2 as a result. So minus 1, 0, 1 into m. Sketch this graphic is very simple. It's very easy. Okay. So the x-axis, f of x, which is equal y, and this is the image, and this is the domain. So for each value of the domain, we will get a different value on its image. So now we are getting a injective function. So is a set of the real, which is injective, into other set of the reals. Minus 2, minus 1, 0, 1, and 2, minus 2, minus 1, 0, 1, and 2. Injective. Okay, so minus 2, sorry, minus 1, minus 1, minus 2, 1, 2, minus 1, minus 2, 1, and 2. Okay, so for minus 2 on the domain, we will get minus 2 on the image. Minus 1, we will get minus 1. Sorry. Minus 2, we will get minus 2. Minus 1, minus 1. For 1, we'll get 1. And for 2, we get 2. Okay. Okay, and again, trying to point for some properties of this function. There are things that we can point just by looking at it, and some other things we need to prove with some math. And just by looking at it, doing a visual analysis, we can say that is a function that is symmetrically It's, it have this symmetry, symmetrically. Also, we can mirror such a function, and we can also say that is increasing function. And this is for a positive, a greater than 0. Okay, now let's uh, try to plot this in Octave right here in this environment. So we were doing we were creating variables like x min and x max, and creating also a variable to storage um, the x-axis. We are using the function line space to draw this x-axis, and we are passing as argument to this function line space these variables which we can storage on it, um, the ranges of the x-axis. But we can do this directly. Instead of use variables, we can directly pass as argument to this function um, the ranges of the x-axis, its limits. So minus let's use minus 2, and is ranging from -2 to 2, and now we pass also the number of points that this x-axis will be drawn. And for now, let's use also the linear coefficient. Let's leave here, and 1, which is a positive linear coefficient. And now let's create the function itself, y, which is equal x. A times x, okay. And now we just need to ask to the Octave to pull out this function. So x and y. Okay, let's see. Okay, we made it. And there we have it. A linear function ranging from -2 to 2. Okay, and on the image and on the domain, and on the minute on the image, also ranging from -2 to 2. Okay, that was easy, huh? So let's keep going. Let's continue. Now we will sketch with a linear coefficient negative, which means that is less than 0. So let me just copy this. Now the linear coefficient is a less than 0. Okay. And now as this coefficient is a less than 0, x will assume y will assume negative values. So for example, right here, -2 times -1, because of this negative value, we get to 2 positive right here, 1, 0, and 1, -1. So we get -1 and -2. Okay, so for x equal -2, we get a positive 2, -1, we obtain 1. For x equal 1, we get -1. And for x equal 2, we get -2. Okay. Okay, now we get this curve, which is decreasing. The slope of the curve is negative. Right here, the slope of the curve is positive, a positive slope. Positive slope. And right here, the slope is negative. And these properties, it remains. We can say that is symmetrical. Just symmetrical. We can mirror such a function, and right here is decreasing. This function is decreasing. Now let's try to, we just need to change this linear coefficient, and we will get this curve with this negative slope. So now the slope of the curve is negative, a negative slope. Let's see. Exactly. Okay, we got the function now still ranging from -2 to 2 on its domain, and on the image also ranging from -2 to 2. And what we can also affirm about this is it's we can see a proportionality, and we can prove this again. Let's say now is a function, for example, 2x, and 2 is again the coefficient, linear coefficient. Linear coefficient. So for minus 2 we get minus 4, minus 1 we get minus 2, for 0 we got 0, for 2 we got 4, and for 1 we got 2, and for 2 we got 4. And we can verify actually this proportionality. And proportionality is something that we will explore on this video using a real data um, from a conversion of reals to dollars. So 1, let's say 2, 4, minus 2, minus 4, 2, 1, 2, minus 1, minus 2. Okay, we know that is a positive linear coefficient, so we know that the function is increasing. And if it was negative, so the function will be decreasing. But something that we are pointing right here, it is the proportionality, this property, proportionality. This property, and I'm pointing this because now we will explore again, trying to adapt such functions to real world problems. We have this data right here, which is the conversion of the real to the USA dollar, and we got this percentage right here, which is the dollar exchange rate. And for us doing the connection with the linear function, this is for us the linear coefficient, this percentage, which is the dollar exchange rate. So what we are going to do right now is trying to import this data into Octave. So first type clear all to clean up the Octave memory, and then CLC to clean the command window. Now we need to load a package, so type pkg load IO. Now type data, because we will start on this variable that we are naming data. This data we will import the data and store it on this variable data. And this Excel file it got the extension CSV. So type CSV and read. And with this command, we will read the Excel file. And what we need to do right here is pass as arguments the path in which this file is localized. So copy the path of the document, and this data is available on a website called Investigated. So Investigated. uh, investing, sorry, is available on the website called investing. Investing. This is a real data. Okay, so go to this website and try to download this this data. It's available for free. Okay, and again, now on inside of these parentheses as argument, we need to specify the path of in which this file is localized. So right here, I will open my files, download, and I got the file right here. So I click on it and copy the path. And now I paste right here. Okay, and we need to use forward slashes. So we need to change right here for forward slashes. Okay, now enter. Okay, very nice. So as you can see, we are importing this data right here into Octave. And now we can plot this data so we can see um, this data instead of do a analysis of the numbers. We can do a visual analysis and see the points in which this exchange rate is increasing or decreasing. So type plot and inside of the argument data. Okay, very nice. Now is looking like more a signal. So as you can see, we got some sections of the signal. So we can say that is a sum of successive increasing and decreasing linear function. If we if we face this way, if we approach this way. So right here is increasing, this section is increasing, right here is decreasing, sometimes is very close to a constant function, but most of the time is increasing and decreasing, because yeah, we will get points where is constant if let's see right here on the data, we are collecting this data, let me see, 1 week, 2 weeks, 3 weeks. So we are collecting approximately 3 weeks of the month 6, and let me see, just 3 days of this month 7. So we are getting this exchange rate, dollar exchange rate, this percentage, and this percentage we can say that is our linear coefficient, and most of the time it's being negative. So right here is negative, right here is positive coefficient, linear coefficient. Okay, so we can, if you wanted to do a validation, take a conclusion of some specific month or day, we can isolate some section, and we can, if we were able to isolate portions, sections of the signal, uh, we can specify, uh, for example, for some time, let's say day or month, um, um, the quantity in money that we are obtaining, and of course it will depend upon of the linear coefficient, which is depending on of the section that we are isolating, will be positive or negative, and this linear coefficient is the exchanging rate. We are doing a conversion of real to dollar. This is a percentage. Okay, now you can see how we can approach signal processing using functions. Again, this is not a conventional way to approach signal processing. We are again just trying to build a strong intuition. I say that signal, they are real world signals. They are not always well behaved, and as you can see right here, we can face this as a signal, and of course it's very clear that it's not well behaved. And yeah, but with this linear function we can take some conclusions, and is a method, is a way in which we can approach the signal. Of course we got other um, ways to approach this, but this is one of the ways that we can use. Okay, for now it's all. I wanted to um, comment this data with you with more details on the income videos with if we got the opportunity, because we are running with this content. I wanted to approach trigonometric functions, and this is will be the beginning of uh, the real signal processing, where we will approach sinusoidal signals, sine function, cosine function, and start to, for example, discretize the signals. In this way, uh, again, right here on this example, when we discretize signals, we can isolate parts of the signal, we can separate frequencies, or even cut off some amplitude or frequencies. So we are now developing filters, things of this nature. Okay, so yeah, again, I recommend to you to go to the investigating website and download this data and try by yourself to plot this data. And yeah, right here we are doing just basic things. Actually, we can plot uh, the signals individually, not all of them, and take some conclusions. If we use more programming language on the Octave, and this is we will see further having the opportunity. For now, it's all. Thank you.